Our series, Climate Change 101. How many new people are here who haven't been? I'm going to get some newcomers. So, for those of you who are new, welcome, and for those of you who are returning, thanks for coming back again. Today's speaker is Professor Jeff Mount from UC Davis, about climate change in the Sacramento-San Joaquin Delta. I'll turn it over to Jeff.
Great. Thanks, Terry. Okay, so if you can't hear me in the back, speak up. Raise your hand and yell at me. Actually, we have an interesting challenge. So this is all new technology for me, so I'm sure I'll screw it up right off the bat. Okay, well, real quickly, let me introduce myself. I'm Jeff Mount. I'm the director of the Center for Watershed Sciences at UC Davis, and I'm one of a group of authors who have been roiling the waters about the Delta, particularly in the last year, and I'll refer to that in a second. Since this is a climate change talk, I thought what I'd do is I'd focus on climate change and what it does to the Delta, and then hopefully have some interchange with you about that. I have some fairly incendiary things, and those of you who know me are not surprised by that. I have a couple of incendiary things to say about this. I'm going to talk about 4 principal drivers of change: subsidence, sea level rise, changes in inflows, and seismicity. I'm also going to talk about basically the inevitable in the Delta, how it's going to change. Then I hope at the end I'm going to talk a little bit. Again, this is intended to be interactive. Talk a little bit about the fact that we need to deal with the Delta in a different way. We need to think differently about the Delta, and it's going to be a huge challenge for people to do that, politically, socially, intellectually, emotionally, physically. I don't know, all of those things together. Okay, so first of all, what I tell you is some of the work that I'm here is from the Elephant in the Room that we released a year ago with Jay Lund as the lead author, one of my colleagues at UC Davis. And this is this report, Envisioning Futures Delta. We are currently working on a sequel to this, part 2, which will come out in June, and it is essentially an evaluation of the options we raised in this initial report. And you can find that online at either the Watershed Center's website or the Public Policy Institute of California's website. Okay, look, new technology. Pay no attention to the small man. There we go. Here we go. Okay, let me just remind you of the obvious. Everybody in this room knows the Delta. You know something about the Delta, but I do want to remind you that contrary to what you might read in the newspaper, there's a whole lot to the Delta. And most people, and including some politicians, think of the Delta as a water supply feature with an ecosystem problem. I tend to view it as an ecosystem with a water supply problem. There's much to this Delta in terms of a series of ecosystem services beyond water supply. Of course, there is the in-Delta agriculture. There is this ecosystem. No matter what you think about it, it's an ecosystem. There's an ecosystem out there. You just don't like some of the parts of it. There's tremendous amount of infrastructure in the Delta. One major aqueduct, of course, that feeds the Bay Area. Three highways, one major railroad, a gas pipeline, electrical lines. It is a center of recreation for California and will continue to grow as a center. And then, unfortunately, it also is becoming an area of interest for housing. There is a proposal for more than 130,000 new homes in the Delta proper, many of those homes as much as 5 feet below sea level, proving yet again we learn nothing from our mistakes in the past. Okay, well, let me just to real briefly also remind you something else about the Delta, which is relevant to the concept I'm going to hit you with here overall, okay? This Delta lies at the confluence between 2 of the biggest rivers in California, the Sacramento, which is the most important river in California, and the San Joaquin. So it lies at that confluence between those 2 rivers, and of course it lies at the head of the San Francisco estuary. No more dynamic spot in California, period. It changes seasonally. It historically changed quite dramatically. You couldn't draw a line between the San Francisco Bay and the Sacramento and San Joaquin River because it constantly moved in the course of a given year during the flood season or during the summer. So a very dynamic border between the two in every year and certainly between years. Remember, this is a place that this Delta used to get really dry and this Delta used to get really wet. So lots of interannual variability, a dynamic, constantly changing landscape. Now, how do you manage something that changes all the time? Well, I go snowboarding with my son, to give you an example of this. And these are two strategies. My son is limber, 17 years old, incredibly flexible, and as he goes down the slopes, I look at him and I say, that is the definition of resiliency. Okay? When he goes over a bump or ducks under a tree, he's constantly flexible and moving. Then I go down the slope, and I'm on a snowboard, and I'm stiff, I don't bend, I just go down the slope, and I crash. And then I get up. I am rigid. He is resilient. So in our design for management on this system, they used the analogy of me, the old stiff guy, in building a rigid, not resilient system that is not able to flex with change. And respond to change. And I'll highlight that as we go along. So, rigid, not resilient. That's what I want the emphasis I want to get. And of course, this rigid, not resilient system reflects policy. The policy of the last 70 years. The policy of the last 70 years has been to try and make the delta hold still. It does not move. It physically does not change. You have 1,100 miles of levees. The principal tool of management for the delta for over the last 100 years is to keep it fixed in space. And then we keep it fixed in time by our carriage water releases from our reservoirs. So fresh all the time, unmoving. I can't think of a more rigid system than that. Problem is, you have 4 climate change related drivers which are basically pushing on this rigid, not resilient system. Those of you who know the literature on resiliency, whether it's engineering resiliency or ecological resiliency, know that systems that lack resilience tend to undergo punctuated change. That is, what will happen is they'll be static and unchanging for long periods of time, and then they will reorganize with dramatic reorganization. And it is by the time you are done today, I didn't get the name Dr. Doom for nothing. By the time you're done today, you'll see how I think this change is going to occur. Nothing like good controversy at one of these talks. The nice thing about climate change is it's not in it for everybody. Okay. So of course the big, and it is a climate change related driver in the delta is subsidence, and this is the fundamental transformation of the delta from a 700,000 acre tidal freshwater marsh in which there was extraordinary complexity within it. That is physical and chemical and biological complexity, to convert it to what it is today, which is a system of 1,100 miles of levees that basically surround subsided islands. And of course, the issue in the subsided islands is you have a volume of space. You have space that lies below sea level today, which is roughly equal to all the material of Rome. The construction of, you could dump all of Rome, century upon century of the construction of Rome, into that hole in the ground that is the delta, and you wouldn't fill it. You could have 2 hydraulic mining eras come back to California, and you still wouldn't fill it. This is quite a hole in the ground, which was created by subsidence in this system. And of course, that subsidence is a function of the fact that we reclaimed those soils. And we reclaimed those soils principally by creating levees and then building ditches around the edges of those what were former islands and draining those soils and exposing them to oxygen. When you expose them to oxygen, you change the microbial communities and you burned up the peat. So 75% of the subsidence that you see is principally gone off into the atmosphere. 2.5 billion cubic meters gone into the atmosphere. Now, we were just having a little conversation here earlier about how much CO2 that represents, and I sat around and drank beer with a couple of graduate students, and we worked it up, and we came up with a number which is wrong. Okay? It's wrong. I'm on the web. It's wrong. But it's big. And I mean, it's really big. As in about 5 years of the total carbon production of the United States kind of number that we have at current rates. Big number. Lots of CO2 into the atmosphere. Now, the delta is not subsiding as fast now. It's because of the reduction in the amounts of organic matter and, most importantly, better farm practices. It's not creating as much CO2 today, so much less today. But it is that subsidence of the islands and the transformation of that landscape and the need to constantly build bigger and better levees been the primary driver. Now, why do you care? Well, here's why you care. Here's why my mother cares. Aha, this has got to be done. First technological failure, pay no attention. Okay, so normally this animation would run its, not animation, would transition itself. Okay, what happens when you break one of those levees? Because they are so deeply subsided and you have such high hydraulic head, that is the difference in elevation between the water surface on the outside, which is about at sea level, and the interior of the island, which is as much as 25 feet below sea level, that water rushes in to fill that hole. And as it rushes in to fill that hole, you get basically salt water pulled in from San Francisco Bay all the way into the delta. And of course, water supply for 25 million people is polluted with salt. That's basically the function. This is why you worry. This is why the director of DWR worries about this. This is why the governor worries about this issue. If you had a failure of multiple levees during the summer in particular, you would be drawing the salt water into this system. That's why we sweat the levees in the delta. Okay, now I want to get to, so why was that, it got anything to do with climate? Here's why it has everything to do with climate. It turns out the rate at which subsidence takes place is a function of your land use activity, how much you drain it. But it turns out one of the terms that's extremely important in that rate is temperature. So as temperature warms up, the rate of oxidation of the soils goes up, can go up quite substantially, and your rate of subsidence can increase. Now, we have a limit on all of that because we burned up more than half the organic matter which was accumulated in the last 5,000 years in that system. Since the mid-Holocene, as sea level has risen, and basically you would have created a lake in this system, but what happened, it was filled up with organic matter, in the Tule Marsh organic matter. Well, we've removed about half of what was there. Okay, so now comes the second part, which is the second driver in all of this. And that is, of course, sea level rise. Again, much discussion about sea level rise in the media, much discussion on the most recent IPCC report that has come out. But I got to tell you, in the Delta, everything is tied to sea level because it is a tidal estuary. I mean, it's an estuary with tides in it. And it's a tidal freshwater marsh in that system, and tides are the primary driver. And all of the hydrodynamics, habitats, everything is related to sea level. So as sea level rises, this system should change, right? It doesn't change. Sea level's been rising over the last century, of course, as these levees were evolving. Now it is a rigid, not resilient system, fixed in space. And so you have a set of levees. That's it. They can't self-adjust. Okay, so sea level is rising this system, and all our predictions are substantial sea level rise for this century. We are arguing about the x-axis, not the y-axis. And what I mean by that, what we are arguing about on sea level rise is not if, but when. Okay, it's not even how much, but when. So it's the x-axis we're fighting about. That's my geek out for the moment. All right, so what does a 1 meter sea level rise mean in this system? Well, it turns out we've reclaimed 95% of the system. So 95% of this area has been already got levees around it. So there's not much room for further expansion as sea level rises. But this map, which is courtesy of Noah Knowles at the USGS, basically shows you what a 1 meter sea level rise does to the system. I will tell you flat out now, if you hold still and have a 1 meter sea level rise to the system, all of the islands of the Delta flood. They all flood. They're all within the National Flood Insurance Program's 100-year floodplain anyways. They all flood, but you also can see that you get what's called a coastal rollover, where you will get expansion of those areas which are intertidal. So you will actually inundate those areas. Delta, so up the Yolo bypass, okay, moves up the Yolo bypass, would move up the lower San Joaquin if it could. It was allowed to. So sea level rise. Yes, please ask questions, by the way. This is tended to be more like a classroom than a public lecture. Oh. Yeah, okay, so yes, that's correct. Yeah, okay, so this is the beauty of technology. Yeah, those areas that are white are presently underwater. Okay, so let me repeat. So the white that you're seeing on this diagram, again, this is from Noah Knowles at the U.S. Geological Survey. The white are the areas which are currently underwater. Okay. So the blue is the new areas underwater which are below present mean water level. And of course, the red is the areas that would be underwater with a 1 meter rise in sea level. Why do I care about a 1 meter rise in sea level? Simple. It is the latest projection of sea level rise by 2100. Okay? The IPCC reports, we can talk at length about this, actually lowballed the amount of sea level rise. There was a lot of criticism, a lot of scientific papers written afterwards that they had failed to consider all the factors. Remember, the IPCC numbers are a vote, essentially a vote, and so they were done conservatively. The Independent Science Board, the Cal Fed Independent Science Board, wrote a memo this last summer which basically said for the purposes of planning in this system, we should count on about a 1 foot rise in sea level by 2050 and a 3 foot rise in sea level by 2100, approximately a meter. Okay, and please ask questions, and just somebody has to remind me to repeat the question. Okay, so sea level rise is unavoidable. In fact, I want to emphasize sea level rise and how that translates into the delta, because there's lots of myths about how sea level rise will translate in the delta. I've heard people say, oh no, sea level rise is not such a big deal because it won't be that important in the delta. And you always no. If your island is 25 feet below sea level and it rises 3 feet, you're now 28 feet below sea level. What does happen though is the effect of tides. Okay, is damped as you get farther into the eastern part of the delta and the far northern and southern part of the delta. So what really happens with sea level rise and the way it will impact the delta most dramatically is not just because you'll have an average water surface elevation, which is higher, but it's the amplification of those high tides, those rare high tides. That's where it's going to have its. And of course, that will be principally, the biggest impact will be in the western and the central delta. I'll show you some maps of that in just a second. Okay, so subsidence and sea level rise, and now number 3, the one we all know about and has been talked about plenty in the news, and that's the changing inflows to the delta. We keep, again, we're quibbling about X in a lot of this, but depending on which hydrologist you want to listen to, we are in a period, okay, the period for roughly 1900 to 1950 was what I like to call the kinder, gentler hydrologic period in California. And that is that our variations were modest. We had a big drought in there, but our overall fluctuations were relatively modest. Post-1950, I refer to the bipolar era in California climate, where we get big extremes. We got the record drought, we got a record wet, we had the record long period of wet and a record long period of drought. That's what most climate folks will tell you is the future condition for California. And then the people who take these global circulation models and actually downscale them and try and drive climate models for California continuously point to the same conclusion. And our own work has pointed to that conclusion as well. Are we having a fire alarm? Okay, we didn't do it. Our own work points to that same conclusion as well. We are seeing a shift, a current shift, and a progressive shift in the rain-snow mixture, the timing of runoff. We're shifting more and more to the winter simply because we're getting more rain and less snow in the system. So that's changing the inflows to the delta. And no matter how you shake it, when you plot that up, you see that you are seeing progressively higher winter inflows into the delta. And in fact, the standards that we currently use for the delta are so out of date. For example, what's called the Hazard Mitigation Program standards, which are all tied to 1986 water surface elevations for the 100-year flood. It's time to update that hydrology, and we know what the answer is going to be when you do update it. We're getting bigger flows. So here's a concept I want you to take as part of this rigid, not resilient system. The hydrology of the past is not a very good predictor of the hydrology of the future, yet every way we do it these days, in terms of the way we set our standards, is entirely dependent on the hydrology. Okay? A statistical analysis of the hydrology of the past. Everybody in Sacramento should know that well. Okay, so subsidence, sea level rise, changing inflows, all 3 of these are driving against this rigid, not resilient system. My argument is those 3 factors are going to cause a fundamental change in that system. Now, the system already experiences an average levee failure of about 0.86, if you look at it. I mean, but in the central delta, it's about 0.6. It's roughly a 60% probability that you'll have a failure every single year in the system. That's the average annual failure rate of levees within the system. What I'm telling you is you're going to have an increase in the rate of failures. We all remember the Jones Tract failure as one of our examples of a failure, and what they look like. Significant consequences associated. Okay, at UC Davis, as part of our troublemaking efforts, we've sort of gone at trying to get at what is the probability of failure of these levees, and what is the probability of a big-scale reorganization. I don't want to go into the details of that. We have developed a very simplified probabilistic model for failure of the levees within the delta and what it means for individual islands. And basically, we looked at a subset of 36 islands. This is stuff that will be released in a few months from us after it's gone through peer review. So everything you're hearing about this stuff is in its most draft form, okay? Because it hasn't gone through peer review yet. But after it's peer reviewed, it'll probably still look pretty much the same. And basically, what we did here is we looked at 36 different islands within the delta, and we asked ourselves this usual approach: what's the probability that an island would fail in a given year? We developed a simplistic model for that, which is based on head and the length of the island. And we came up with an annual probability failure. It's just when you go and you start talking, and I've got people like Ron Stork here in this room who know that when we get into discussing probabilities with people, their eyes glaze over and they just, so I'm going to flip it on its, so I flipped it on its head for today's presentation. And I said, well, let's ask the question, what's the probability that a specific island or all of these islands won't fail in a given year? And what's the probability that they won't fail for the next 50 years, or the next 70 years? I mean, so if I ask this question, I usually use 50 years as my benchmark, by the way, for lots of reasons, not the least of which is my 17-year-old son, who will have a 50-year working cycle, and he'll be 67 by the time that 50 years is up. And since I will have plundered Social Security, he'll be working for an additional 10 years after that. Me first. So I asked that. I turned that around and I asked that question. So what you see on this screen here, and those of you who are watching this on the web, is essentially the array of probabilities that we calculate for failure of the islands due to flooding. Now, this is three types: overtopping the levees, seepage through the levees, and seepage underneath the levees that cause failure. So what I'm telling you is your worst islands. Let's take your median island, your average island. I mean, not average. So I mean your median island of all 36 of them, right in the middle island. What is the probability that it won't fail in the next 50 years? Well, it's about 3 in 10. About a 30% probability. Those don't seem like really good odds. You can turn that around on its head and say, you mean it's a 7 in 10 probability that island will fail in the next 50 years, and half of the islands have worse than that. So it really works out to a sort of simple way to think about this. It's a roughly 7 in 10 probability that half the islands will fail in the next 50 years. That's a simplistic way to look at it. That's a good planning. That's good for planning. And what I'm telling you is that this process of rigid, not resilient, and being pushed by sea level rise, subsidence, and changes in inflows, pushing these islands to have increasing failure with time. Whoops, I pushed the wrong. Hang on. Okay, thank you. Okay, the question was, this doesn't consider climate change, this is current conditions. It gets worse. This is like, yeah, sorry, you got me. I'm Dr. Doom. Okay, so we actually, because people might accuse me of being a fearmongerer and inflating these numbers, we actually just held it constant for that period of time. And now we've developed an algorithm which accommodates climate change, and you know what direction it pushes it all. But these are the factors that are pushing on it today. So here is a simplified animation based on this simple model that we developed for island failures. And what it does is it looks at when an island passes a threshold of a roughly 3 in 4 probability that it will fail in a given decade. What you see is here's what the configuration of the delta looks like today. This is the do nothing scenario, by the way, which is wrong. We won't do nothing. That's a double negative. We'll do something. Okay, so this is today. This is 2030. This is 2050. This is 2070. And that's 2100. Okay, and now there's some goofiness in the model that leaves a couple little islands surviving and all of that, and that's simply because their levee lengths are so short. You can pretty much wipe those off the map. Okay, so that's just a sort of conceptual, that's the do nothing. That's if you sit there and do nothing, that's the eventual way it's likely to be in terms of failing of those. But wait, I'm not done. Okay, here comes the wild card. And that is, the delta has not been shaken. This is not a climate change feature per se, but it is so relevant to the climate change modifications people want to make in the delta. You're going to hear lots of talk in the next couple of years about upgrading the levees of the delta, and that upgrade would involve adapting to climate change and how we're going to deal with climate change. But one part you can't get away from is the fact that the delta has not been shaken for 100 years, not severely shaken. It has been shaken by modest earthquakes of some distance away, which did cause damage. Contrary to lore that you hear, it did cause damage in the delta, but there were no levee failures associated with earthquakes. But remember, 100 years ago, in the 1906 quake, levees were about that tall. Okay, I'm giving about 3 feet. No, I'm giving about 6 feet. Right? No, levees were about 3 feet tall. I so wanted to be tall. I was 100 years ago, they were nothing. They were just little bumps on the landscape. And now they're 30 feet tall. Okay, so levees have gotten much, much taller. And they haven't been shaken. There isn't a seismologist in the business who won't tell you that the delta is ripe for a major set of ground accelerations which will cause levee failures. And in fact, this is the figure that URS put together, which I like to call the tombstone figure. And what it's showing you is that we have been in an extraordinary period of quiescence, earthquakes, very mild and far apart. And what that means for those of you who are the geologists, and I see a couple of them in the room here, is you know what happens during long periods of quiescence. We're building strain on this system, and the U.S. Geological Survey has repeatedly warned us we're building strain on the San Andreas system. And remember, the San Andreas is a system of faults. Okay, it's many, many faults. And we are looking at very high probabilities for high ground accelerations. Now, it turns out that DWR has commissioned a very large and complex report, and I'm going to steal a little bit from it. And this is the Delta Risk Management Strategy. It's in draft form right now, undergoing revision. So I just want you to know that it's not done yet, but when it's done, it's going to give us a heck of a lot of precision on this question, the specific question. But I'm telling you, earthquakes are the wild card in all of this, and it isn't climate change, but it does intersect directly with climate change. So take my simplified UC Davis model for what's the probability these things won't fail. Now you take the Delta Risk Management Strategy model and you superimpose it. You can't read that, so I'm just going to put an arrow in here to show you what I mean. Essentially, remember that median, that concept of the median island? Well, it's roughly 50-50 chance that the median island under the model we developed would survive for 30 years. Roughly 50-50. That means half of them would be less than that. Okay? Half of them are worse than that. When you factor in the seismic risk, it's, at this point, a 20% chance that half the islands will survive 30 years in this system when you add in the seismic risk and the slightly higher flood risk factors that come to Delta Risk Management. Point is, I put this really simply a few years ago and got in a lot of trouble for it because one has to be really careful about simplifying probabilities. But I asked the simple question: what is the probability that there will be, in the next 50 years, a very large flood which will actually destroy many islands in the delta? Well, it turns out the entire delta is mapped into the 100-year floodplain. And the probability that over the next 50 years the 100-year flood is going to occur is a roughly 2 in 5 probability. Roughly 2 in 5. Then I asked the question, what's the probability that a 100-year quake is going to occur in the next 50 years? Probability is the same. It's roughly 2 in 5, right? And a 100-year quake will probably cause a loss of anywhere from 5 to 20 levees in the system. Okay, what's the probability that either of those is going to occur in the next 50 years? Okay, that probability is 2 in 3. Okay, so that's a good planning number. Even though it's simple and wrong, it's a good planning number. So it's a 2 in 3 probability you're going to have a major reorganization of it. Okay, so since at UC Davis we're knocking ourselves out, and I just can't, you know, there isn't an academic anywhere who can't resist showing their draft results. And I want to remind you, these are draft results. Usually, by the way, that's where I end the talk with the title, You're Hosed, or something like that on it. But we want to go and look at some of the consequences of this and what it actually means. So we really have matured our thinking to actually start worrying about the consequences of stuff. And so my colleagues, I take no credit for this, my colleagues have been busting their tails doing a lot of modeling and consequence modeling, both economic consequences as well as hydrodynamic and water quality and environmental consequences. And I want to give you some of the preliminary results that we have here. And this is going to be a bit of a technological challenge because I'm in a system that doesn't work normally as my computer does. I'm going to talk about a couple of places here. In particular, I'm not going to talk about Chips Island. I'm going to talk about Emeton. And when I say Emeton, think Rio Vista, near Rio Vista. Most of you know that. And when I talk about Jersey Point, of course, you all know that's on the San Joaquin, on the far western part of the San Joaquin River. When I talk about CCWD, I'm talking about the Contra Costa diversion that they use. Remember that group is almost entirely dependent on the Delta for its water supply. And then I talk about banks. I'm talking about their diversions that come out of the South Delta at that point into the State Water Project and the Central Valley Project. Okay, interesting. And also, we've taken a couple of questions. Okay, if I think there's going to be all these flooded islands, what's the consequence? We have been told, okay, that is conventional wisdom, tells us it's a disaster. And that's what you've heard on the news and everywhere else. Flooded islands are a disaster. We have to hold the levees together as this rigid, not resilient system because we need it to protect the state's water supply. Okay? That's conventional wisdom. It's not true. There's nothing like beating up on conventional wisdom. Let's go ahead and beat it up by seeing if I can possibly get this animation to work. One of the things we've looked at, whoops, I think I need to go to the next one. One of the things we've looked at is what happens when you flood the islands. And we've done, we actually in DREAMS they've done this, and we've taken up some of this modeling work and are starting to work on it now. We've asked some very basic questions. What happens if you flood the western islands? What happens if you flood the northern islands, eastern islands, and the southern islands, and the various combinations that come between? And I'm not going to go through all of that because it's mind-numbing stuff to go through most of it. But what I am going to show you is one animation, which is basically comparing what happens when you flood the western islands versus the 20 major islands of the Delta. Hang on, let's see if I can get to that animation without screwing this up. I'm almost certainly going to screw it up. But I have technical help here, so that's the good news. Is it working? Yes, it's working. Okay, this is an animation of basically what happens when you flood up all these islands. Now, I've flooded up these islands, and I've compared the western islands, just flooding the 5 western islands, to flooding all 20 islands that you see here. And one of the things that happens when you take a hard look at how this system responds to flooded islands is this notion that all islands are precious in this system. Okay? There are lots of islands you can flood without significant water quality impacts. In fact, it is the western 5 islands, well, let's just say the western 8 islands, which the state knew 20 years ago, that are really the biggest impactors of water quality at the pumps, Contra Costa and Central Valley and State Water Project pumps. And in fact, here is an incendiary, I can't leave here without a couple of real bombs. Here's an incendiary thought. Argument, have to hold all the Delta islands together in order to prevent the loss in water quality at Contra Costa and the State Water Project and Central Valley Project is wrong. And in fact, you can probably let 15 islands go in the South Delta, Central Delta, and North Delta without a major effect. In fact, some of our modeling suggests water quality actually improves a little bit with some of those island failures. The place that it has the biggest impact, the western islands. Western islands are the key feature. Incredibly, those islands which are at the highest risk due to seismic failure. I tell you, this is not a happy story. Not my job to do happy stories. I don't do them well, actually. All right, let's go on to the next one. Again, okay, next. Here we go. Okay, what does sea level rise do to this system? So you are also hearing a lore out there that says we have to invest a lot of money into holding these levees together because they're essential for water supply, and more important, we need to really strengthen them to deal with sea level rise. Okay. All right. Well, what does sea level rise do to this system? So here you have essentially, in order to make an exaggerated point, you have Macintosh. All right, uh, you have sea level rise of 3 feet compared to today. I'm looking at a dry period of time here. This is May 1992, and one of the things you're going to start seeing right away, see that yellow? That's terrible water quality. In fact, 500 is pretty bad in this thing. See where all that yellow is going? On the south there, on the right-hand side, bang, you just cut off your water supply to 23 million people. Sea level rise during the late spring, summer, and into the fall basically jacks up the salinity of the delta so much that you can't use it for water supply. That's if you keep all the levees in place. Okay, so 2 concepts I want to get across. Flooded islands are bad if you're flooding the western delta, but they're probably not so bad if you're flooding other parts of the delta. Number 1. Number 2, sea level rise is a wipeout for water supply in the delta. That is, it significantly disrupts our ability to export water from the delta. I think that's an important issue. It doesn't do that all year round, by the way. And there are parts of the year where the delta is totally fresh. On even normal and wet winters, it will freshen up a great deal. But in those dry years, you'll have a lot of disruption. So to illustrate that even more, by the way, these are called spider diagrams. Jay Lund can be blamed for the diagrams. He can't hear me right now. He said, he came up with these notion of a way of looking at how water quality changes over the course of a year. And so that's why you see essentially the year is essentially moving in a clockwise fashion here. And what we did is we used a series of modeling tools to basically get at what was happening to water quality during specific months of the year under a bunch of different scenarios, sea level rise and flooded islands. Here is no sea level rise. So this is today, 1981 to 2000, and we also have simulated, see how far I got without saying it? Peripheral canal. We simulated a peripheral canal, actually a dual facility, and how it actually might operate. So you'll see there 2K, that's a 2,000 CFS peripheral canal. 7.5K is a 7,500. We actually simulated a 15,000 CFS. There's hardly any difference between a 7.5 and a 15 because of the way we set up the rules for how you can take. What I wanted to show you there is this is today, no sea level rise. Contra Costa on the left, banks on the right. When you see a percentage, that's the number of times it is violating the water quality standard at that location. In this case, the standard for salinity. Now watch as it changes. As sea level starts to rise. See the number of months that now are exceeding. That's a 1-foot sea level rise, and that's a 3-foot sea level rise. Pretty much, you can't operate Contra Costa's withdrawals in dry years with a 3-foot sea level rise, and it even has a significant impact in wet years as well. Same for the banks pumping plant. So significant impact with sea level rise. Okay, well then I also want to look at water quality in the delta itself. We're very interested in the habitat issues, but you've got farms in the delta, and how will they be affected by changing salinity? And the answer is quite substantially in some cases. Again, depending on whether you have an isolated facility or not, as sea level goes up in those systems, you get a progressive expansion in the number of years where they're exceeding their water quality standards, meaning you cannot take water out and use it for farming. Okay, so even in wet years, this is going to have a major impact in that period, July, August, September, October. That's a consequence of climate change. Okay? A direct consequence of climate change will need to be somehow mitigated. So let me give you these initial conclusions on the modeling work that was done. Let me go back to it. Okay, let me explain what that peripheral canal, okay, so we like to call it the peripheral conveyance. What you are seeing there is not the water that would be derived from an isolated facility or peripheral conveyance. It is the water in the channel just outside of the pumping plants themselves. This is assuming an operation of a dual facility where you're continuing to take water out of the delta while routing a portion of it around the delta. And all we did is we reduced, just let me explain real quickly, and I'm glad you asked that, by the way, asked that question. All we did in this case was change the boundary conditions. We took water out of the Sacramento River, disappeared water from the Sacramento River, and we reduced pumping an equivalent amount. So if we took 2,000 CFS out of the Sacramento River, we reduced pumping at Contra Costa and the state and federal projects by 2,000 CFS. That's what it means. And when you see that poor water quality, that's what they would be sucking in at those intakes, even though some of their water might actually come from an isolated facility or peripheral conveyance. I'm glad you asked that question. Thank you. Again, interrupt me as they blow through this. Okay, a couple of things. Here's what sea level rise does to this rigid, not resilient system. Okay, you see increases in salinity everywhere. Okay, there's no part of it is unscathed within this system. Second takeaway of all of this is when you flood the islands, you do not see increases in salinity for the northern, eastern, and southern islands, but you do see dramatic increases in salinity associated with western islands. That's key, because that's a conclusion which will help prioritize how we spend our money. Well, let me ask you then the next question. Now I'm really getting out of my field here, but this is the fun part, because I work with in this multidisciplinary group. What does that mean? How would we adapt to such a thing? What kind of economic optimizations engineering optimizations would we be able to do? Of course, what we're doing right now, and again, this will be released in the next couple of months, is we're doing a whole lot of economic and engineering optimization studies of how we would respond to changes in the Delta. One of the things we're focused on is the extraordinary increase in water treatment costs. Water treatment costs is the part that we don't hear much about, but the fact is you have those precursor problems, byproducts, which are carcinogenic, that are associated things like trihalomethanes, which are associated with treatment of water and can cause cancer. It's a big deal. But we find that the treatment costs end up being very, very expensive, associated. Whoop, wrong one. Hang on. Get a Macintosh. Again. Okay, well, here's a couple of things that we aren't talking about that is a consequence of this increase in salinity. Now, the farmers are going to take the water that works for them into the San Joaquin Valley. But in fact, today, just today, right now, the water quality we have in the South Delta, we are exporting 500,000 metric tons of salt into the San Joaquin Valley that is not making it back out. Okay? It is being stored within the San Joaquin Valley. Remember, the pumps that are in the Delta are in an estuary. Okay? And the water quality in that estuary is generally low. And it has high quantities of salt within it. That salt is going to have a huge impact. In all our simulations, we built a new model for this, for simulating what it actually does economically. We're talking about $800 million a year in lost agricultural production by 2030 in the system. This is a huge deal. And of course, I show you what our current salt load is into the Delta and what it actually costs. Now, if you can find ways to improve that water quality, you will extend the period of time that you can continue to farm in the San Joaquin Valley. You're not going to be able to farm forever. It eventually salts up. But the fact is, there's a big economic cost associated with that salt. And all the trends I just showed you, failed western islands and sea level rise, are going to drive that salt content up. And it's a huge economic impact to the San Joaquin Valley in particular. Let me give you another impact. The other impact, and there are members here in this building from the State Water Resources Control Board that have recently awakened to the fact that they're really important players in this issue in the Delta. Well, if the state board says, tough, we're going to keep standards the same, we're not going to adjust standards. You have to keep those water quality standards as they are. How do you do it? And so we actually have asked ourselves, how would you do that? And one of the ways to do it is reduce pumping, reduce exports. And another way to do it is to increase inflows into the Delta. You've got to remember, we take a huge amount of water out of the system before it ever makes it to the Delta. And that's a politically poisonous thing to ask. But the fact is, we've actually we started doing the optimization analyses on this, and we're finding that it is substantially less expensive to maintain water quality in the Delta by increasing the inflows to the Delta than it is decreasing the exports from it. Very interesting trade-off. Again, nobody likes to talk about that, but that's the beauty of having tenure. Okay, the other issue that nobody wants to talk about, because as I was delighted, I was quoted in NPR the other day as saying, in California, we're a bunch of consensus wimps. I stole that line from Mark Reisner, by the way, fair and square. For those of you who read Cadillac Desert, that's one of the best lines in it. William Mulholland stole the water from Owens Valley, fair and square. I stole it from Mark Reisner, fair and square. The fact is, when it comes down to levies, there have been proposals how to spend the $1 billion that's available from Proposition 1E in the Delta. And that is everybody gets an equal amount, depending on the length of their levee. That might be the way to create consensus, but it's kind of a wimpy way to make consensus because you probably will get almost no benefit spreading it around. I was having a conversation with people from the Corps here earlier. What does $1 to $2 billion worth of investment get you? Well, it upgrades the levees to what's called the PL 8499 standard, which is a federal standard for agricultural levees. It gives you a little bit of improvement. Those failure diagrams that I showed you earlier, they don't change very much. They change a little bit. They shift a little bit, but it's not a dramatic improvement in the reliability of these delta levees. So we have built a levee optimization model as to how you would allocate those resources, those levees, based on what I just told you. Okay, first of all, the land value, depending on the land value, how likely it is for it to fail in the near future, what the repair costs would be if it does fail, and its impact on state water supply and important infrastructure. Of course, what you know to be true is true. It is not a wise investment to put all your money everywhere, to spread it all around. From a state perspective, you're far better making concentrated local investments that are of high value. And seismic risk pushes all of this really screwed our spreadsheet up a great deal. I didn't have a lot of, knowing that I was going to be short on time, I didn't want to get into that. But just basically that conclusion, which I say will be out very shortly, is that we look essentially at how to optimize expenditures and levies, and we find that in fact you are really much better concentrating in a few real critical islands and keeping those islands going rather than spending a lot of money on islands. Okay, so Dr. Doom here has presented to you essentially a concept. That concept is they are rigid. Forces that are acting on that rigidity are going to overwhelm it. We're going to have to make some tough choices about how we respond to that when it overwhelms it. I'm telling you now, we don't have enough money to do it. We will not have the resources to respond equally everywhere, and we will not have the resources to keep the delta looking just as it is now into the future. That's so I will argue, and my biologist colleagues will argue, it's time to start adjusting some thinking about the delta. In fact, if you manage these systems in a resilient fashion, you're going to be managing change. Not trying to manage to resist change, but managing to adapt to change. And that the system might end up looking somewhat different than it has in the past. I think that's the message I want to get across today, is that climate change in the delta ensures that my son, when he retires, at age 77 or whatever it'll be when he retires, that delta will not look the same. It will not be the same delta that I went to when I was 11 years old on a houseboat trip with my parents, in which we hit a bridge and nearly sunk the boat, which I thought was it was very entertaining at 11 years old. The delta is going to look different. What I'm telling you now is the way it will probably look different is that it'll have some large bodies of open water. I think you can safely say that there will be more open water within the delta, which creates a very interesting ecological change in the delta, which will create some management challenges. But assuming that the delta is going to look the same in the future is probably the one conclusion we can reject. It is not going to look like that. Exactly what it's going to look like, that's not so good. I think it's a little tougher to tell you exactly what it's going to look like. So with that, what I'm going to do is show you the there's one approach you could take to the delta, and that's the Alfred E. Newman approach, and what me worry. That has been our historical approach to the delta, and I'm really happy to say that we're not doing that anymore. We are taking a very different view of the delta. You all know here, because you're all in state government, or at least connected to state government, we have two major planning processes going on right now, and that's Delta Vision. It's the Governor's Task Force in Delta Vision, which is taking a very broad look at the delta and the delta in its context within the state. And then we have the Bay Delta Conservation Plan, which is essentially looking, to put it simply, get permits to continue to export water from the delta and try to recover particularly the listed species within that system. Never in the history of this system has there been more concentrated political focus on the delta than right now. So it's extremely important that if the one message we take away from all of this is that because of climate change and occurs our legacy of activity, the delta is going to look different than it does today. Just how? how different, and what's going to look like. And with that, I will answer questions. Thank you very much. Sure. Well, okay, so what are the major options for increasing flow into the delta? That is what this one, okay, those of you who are familiar with the model that we're using, which is the Calvin model, which basically simulates all water operations within the state, throughout the entire state, and then actually puts value on it. The model makes some assumptions, one of which is wrong, and that is that we'll make rational, economically based decisions about how we move water around. Three principal ways. One is conjunctive use of groundwater, that you actually can go ahead and do some storage of groundwater in the ground and actually use that groundwater during periods of scarcity so that's a storage. The model does not predict increased reservoirs upstream as a way to deal with this. It's mostly using groundwater as a place to. It is a pricing phenomena, and that is, it might be worth it for, say, somebody, we won't mention any names, but they might be located south of the delta, to actually buy water north of the delta to allow it to come into the delta to keep the water quality standards higher. So that's another one. And of course, the other is there's a couple of factors that we have to consider is changing cropping patterns. As water gets more expensive in this system, you will change crop patterns and you probably use less water. So those are the options, principal options. The model does not suggest that it is. Hope the governor's not watching. The model does not suggest that it is optimal to increase surface storage. Okay, so it doesn't figure that way. It always goes to the economically optimal approach in this case, and so it's economics. Don't advocate building. Just economics. Actually, he was first. Okay, so you are not alone. Okay, let me repeat the question. I mean, I'll summarize your question is basically, we've had a historical methodology that we use for basically the way we do flood management. And again, that's a statistical analysis of historical hydrology, high water marks, a variety of approaches. But all bets are off because that climate is different than we think than the climate that's coming. Yet our uncertainties are huge as to what that climate might look like, particularly things like high flow. I mean, do they get bigger than we've seen them in this system? Do they get a lot bigger? Or do they get a little bit bigger? Do they come more often? So, the answer is, this is a national, this is an international discussion that's going on. The Dutch think they have it all worked out. I've looked at the details of the way the Dutch project climate change and how it changes their hydrology, and it's laden with a whole lot of coefficients and assumptions. So we haven't got that part worked out. I mean that in all sincerity. So what you now do is you have to do the engineer's approach, the true engineer's approach, which is you make systems that are more robust, okay, that can actually handle these extremes much better, or you make good land use planning decisions. But right now, we do not have a method to answer your question to basically predict what the future flows will be like. Okay, sorry. Those are conceptual, just so we make sure. Right. Okay. These are okay. So what happened is I put up here just an answer to the question to put this back up. These are 3 scenarios. These are not predictions. They're scenarios. There's a big difference. Okay. Those are 3 scenarios that I built some time ago to basically do some basic analysis of consequences. Those are scenarios, not predictions. Important, you know. Josh. Okay, so the question is, how does, let me, to simplify that, how does evaporation or evapotranspiration, which intends to increase under increasing temperature, create some feedbacks in this system? And I have not accommodated any of that. We have our own climate model for runoff in this system, which actually accounts for increases in evapotranspiration and its changes in timing and nature of runoff.